I would like to thank you for inviting me, and I am grateful to all the professors and students who have come to attend this seminar. It is a great honor to present some of our recent work on how artificial intelligence can be used for engineering design and how these methods can be applied in practice. This has been one of our principal research directions for approximately 9 years. My presentation contains 4 parts. First, I will explain why we began this research and introduce the background and several key concepts. Second, I will discuss the progress we have made in generative AI design algorithms. This part is mainly concerned with the scientific questions. Third, I will show how these technologies have been extended to different engineering domains. Finally, I will present several conclusions and thoughts for discussion. Let me begin with the first part, the research background and the reason greater automation is needed in engineering design. At present, most engineering design is still performed through intensive human effort. Engineers work very hard, but the efficiency of the design process is still insufficient to satisfy the rapidly growing demand for construction and infrastructure. This is not only a problem in China. It is also a problem in the United States and many other countries. Construction productivity has not improved at the same rate as productivity in many other industries. We therefore need to look for a fundamentally different solution. In recent years, all of us have heard a great deal about generative AI. The essential concept is illustrated very clearly by the faces on this slide. After learning from a large quantity of data, an AI model can generate something new. The 4 faces shown at the bottom were generated by combining features learned from the faces above. They are not photographs of real people, they are entirely generated by AI. Yet they look very similar to people in the real world. This demonstrates the extraordinary ability of generative models to learn a complex distribution and create new, realistic content. When I saw this type of demonstration in 2017, I thought it would lead to a revolution in our industry. The reason is simple. For engineers, one of the most important outputs of our work is the design drawing. From the perspective of a computer, there is no fundamental difference between a human face represented as an image and an engineering drawing represented as an image. If AI can learn from many faces and generate a new face that looks realistic, then, after learning from many engineering drawings, it should also be able to generate a new design drawing that resembles one produced by an experienced engineer. That was the fundamental idea that led us to begin this line of research. 9 years later, it is encouraging to see a similar conclusion in a report released by Anthropic, one of the best-known AI companies in the world. The figure on this slide compares the current use of AI in different activities with its potential future use. The red curve represents current application, and the blue curve represents future potential. Architectural and engineering design show a particularly large opportunity for further AI-enabled automation. Our conclusion, reached from the perspective of civil engineering, is therefore consistent with the broader assessment of the AI industry. Looking back at our work, I think it can be summarized along 2 complementary directions. The first is to push the ceiling of AI algorithms. In Chinese we call this ding tian, reaching upward. As university researchers, we are especially interested in the scientific questions: how to improve representation, learning, optimization, physical consistency, and reasoning. The second is to ground the technology in diverse engineering applications. In Chinese we call this li di, standing firmly on the ground. We do not want the algorithm to work for only one narrow problem. If a task involves the generation of engineering drawings or design objects, we want to test whether the method can be extended across disciplines. The upper part of this roadmap shows the evolution from GANs, graph neural networks, and diffusion models, to intelligent optimization, knowledge, mechanics integration, and finally tokenization and multimodal reasoning. The lower part shows applications extending from building structures to strengthening design, floor plans, dams, photovoltaic support structures, fire sprinkler systems, concrete bridges, and industrial underground spaces. That is the overall roadmap. I will now move to the second part and explain the scientific development of the generative design algorithms. We can divide the development into 4 phases. The first is learning, with drawing learning as the key technology. The second is optimization, with intelligent optimization as the key technology. The third is computation, with knowledge, mechanics integrated computation as the key technology. The fourth is reasoning, with spatial reasoning as the key technology. These stages are logically related. Each later stage builds on capabilities developed in the earlier stages. Let us begin with the first stage, how AI can learn from engineering drawings. Artificial intelligence has existed as a field for more than 70 years, so why has it become so important only in recent years? One of the most important reasons is that modern AI can make full use of large-scale data. The examples on this slide, from AlexNet and AlphaGo to AlphaFold, ChatGPT, and DeepSeek, show how increased data, computation, and model capacity have driven successive waves of progress. If we want to use AI for engineering design, we must also make full use of this data learning capability. This is particularly important in engineering because a great deal of engineering knowledge is implicit rather than explicitly written down. I like the well-known observation attributed to Dr. R. Dykes: engineering is the art of modeling materials we do not wholly understand, into shapes we cannot precisely analyze, so as to withstand forces we cannot properly assess, in such a way that the public has no reason to suspect the extent of our ignorance. The quotation is humorous, but it makes an important point. A student may complete courses in structural mechanics, reinforced concrete structures, and design codes, but that student cannot immediately become a chief engineer. Several additional years in a design institute are normally required. During that period, the young engineer learns from drawings, experienced colleagues, project feedback, in many cases that cannot be reduced to simple rules. If human engineers must learn in this way, AI must also learn from engineering drawings. We therefore began by constructing a very large structural design dataset. More importantly, we established a data flywheel. We made our model available online so that engineers could use it. When users encountered a special case that the model could not solve well, they reported the problem to us. We then expanded the dataset, retrained or improved the model, and returned a stronger model to the users. Through this cycle of use, feedback, accumulation, and optimization, the database and the model became progressively more capable. Using these data, we divided structural design into several levels: vertical component layouts, horizontal component layouts, cross-sectional design, and special component design, including isolation and foundation-related tasks. The divide and conquer strategy allows us to define an appropriate representation and model for each task while gradually building a complete structural design chain. There are 2 principal image-based generative methods available to us: generative adversarial networks, or GANs, and diffusion models. A GAN learns through competition between a generator and a discriminator. A diffusion model learns the inverse of a noise-adding process and produces a design through iterative denoising. Both can learn from existing drawings and generate a new design, but diffusion models have generally given us better global stability and local detail. The challenge is not simply to take a screenshot of the drawing. We must determine how each item of engineering information should be represented in a form that the model can learn. Walls, windows, doors, columns, beams, and shear walls can be encoded as separate pixel channels. Binary values can indicate whether a particular component is present at a particular location. Masks can identify locations at which structural components are potentially feasible. Other design information can also be encoded as channels or feature maps. At the story level, we may represent the plan, column dimensions, beam depth and width, slab thickness, loads, and response indicators. A local region of the drawing can therefore be connected to both component semantics and quantitative engineering attributes. The input is not merely a picture. It is a high-dimensional semantic representation combining geometry, component categories, and design conditions. We also fuse design conditions into the feature space. These conditions may include site characteristics, seismic intensity, peak ground acceleration, building height, number of stories, and structural response information. This enables the model to learn not only what a shear wall layout looks like, but also how the layout should change when the design conditions change. The output should correspond to the architectural plan and the governing engineering conditions. Let me show a typical example. At the upper left is the architectural drawing. The gray lines represent walls, and the green lines represent doors and windows. At the lower left is the engineer's design, the red elements are the shear walls. On the right are the designs produced by AI. Our 2019 GAN result was already generally similar to the engineer's layout, but it contained local defects. When we later used a diffusion model, both the global arrangement and local details became much closer to the engineer's design. Because the design conditions are included in the input, the model can generate different solutions for the same architectural plan. If the design PGA is 0.1 g and the building height is 30 meters, it generates one shear wall layout. If the height is increased to 100 meters, it generates a different layout. If the seismic demand is further increased, the model changes the design again. 2 points are important. First, the model learns the relationship between design conditions and the quantity or area of structural components. Second, while adapting to the conditions, the generated details remain similar to the professional patterns in the training data. The second principal representation is the graph. A graph consists of nodes and edges and is particularly effective for representing topological relationships. In engineering, nodes may represent columns, walls, rooms, or structural joints, while edges may represent beams, connections, adjacency, or other relationships. Graph neural networks are designed to learn from this non-Euclidean data. We converted structural design into two representative graph learning tasks. The first is edge classification. Suppose the nodes represent columns and every pair of nearby columns is connected by a candidate edge. The model determines whether each candidate edge should be a beam. A required beam may be classified as red, while an unnecessary connection is classified as blue. The second is edge feature prediction. Here, the model predicts a numerical attribute associated with an edge. For shear wall design, the attribute can indicate how much of the line between two nodes should be occupied by a wall. A full wall might be represented by 50% at both ends. A wall on only one side might be represented by 50% and 0. Two shorter wall segments with an opening in the middle might be represented by 30% and 30%. These formulations convert structural layout design into learnable graph problems. When we first studied beam layout, we examined existing graph neural network methods and found that none could represent the beam layout rules with sufficient accuracy. We therefore proposed an edge feature enhanced graph neural network called GraphSF. The model combines node information, edge information, and the relationships in the floor graph so that candidate beam connections can be classified more reliably. Given the column layout and floor outline, Graph SF can generate a beam layout very similar to that of an engineer. In tests on 15 real-world frame structures from well-known design institutes, the prediction accuracy exceeded 95%. We also used graph neural networks for shear wall layout. When the structural height or the seismic demand changes, the model adjusts the wall arrangement accordingly. The examples on this slide show that graph learning can capture both topology and the effect of design conditions, including the required quantity and distribution of shear walls. At this stage, our students developed many algorithms for different design purposes: vertical components, horizontal components, cross-sections, foundations, and isolation systems, using GANs, graph neural networks, and diffusion models. I sometimes joke with them that I do not need more papers, but the students need papers, so whenever there is an empty space in this research matrix, they can fill it with a paper. Once the model can generate designs, it can produce thousands of cases at very low cost. This ability provides the foundation for intelligent optimization. There are 3 reasons why intelligent optimization is necessary. First, there is a data quality problem. A model trained on poor designs will learn poor design practice. Second, a generative model is probabilistic and may sometimes produce a suboptimal solution. Third, a purely data-trained model eventually reaches the quality ceiling of its training set. We need a mechanism that can continually generate, evaluate, optimize, and feed improved solutions back into learning. Let us use material consumption evaluation as an example. Conventionally, the quantities of reinforcing steel and concrete are calculated using commercial structural analysis and design software. A single evaluation may take from 2 to 10 minutes. If an optimization process requires hundreds or thousands of evaluations, the total computational cost becomes unacceptable. A senior engineer, however, can often look at a design and estimate its material consumption very quickly, based on many years of experience. We asked whether AI could learn to perform a similar rapid evaluation. We first used AI to generate approximately 4,300 structural designs. Producing so many designs manually would have been impossible, but AI generated them in roughly 1 week. We then used conventional software to calculate the material consumption of these designs and used the resulting dataset to train a surrogate model. The trained AI evaluator predicted material consumption with high accuracy and was at least 500 times faster than commercial design software. It therefore provided the fast, differentiable evaluation capability required for intelligent optimization. With this capability, we addressed the 3 problems just described. First, we optimized the quality of the training data. In the example shown, the quality of the data improved by approximately 13%, and the quality of the subsequently generated designs improved by about 17.5%. Second, we optimized individual AI-generated designs. By combining rapid structural response prediction with material consumption evaluation, the system could produce an optimized, code-compliant design in approximately 10 minutes. A comparable optimization based entirely on conventional finite element analysis could take hours. Third, we established a self-improving loop. AI generated new designs, surrogate models evaluated them, optimization improved them, and the optimized solutions were returned to the training dataset. The effective data volume increased by approximately 7.5 times, and design quality improved by a further 12%. The optimization stage did more than improve designs. It also provided the fast, differentiable surrogate models needed for our third stage, integrating engineering knowledge and mechanics directly into the generative process. When we had worked on generative design for several years, we began to ask a more fundamental question: what is the essential difference between generating an engineering design and generating an article or an image? Most general-purpose generative AI systems are trained primarily for similarity. For engineering design, however, similarity is not sufficient. The design must comply with engineering knowledge and design codes. For example, Chinese design code limits the allowable length or arrangement of a shear wall. A wall of 7.9 meters and a wall of 8.1 meters may look almost identical, but one may satisfy a code limit while the other does not. Meanwhile, it must be mechanically safe. A layout may look realistic but produce excessive interstory drift, torsion, or member demand. As Lord Kelvin emphasized, knowledge becomes much more useful when it can be measured and expressed quantitatively. Our objective is therefore to convert professional knowledge and structural performance into quantitative constraints inside the generative model. The basic formulation of a conventional generative model is simple. We have training data, we optimize the neural network parameters, and then we use the learned parameters to generate a result statistically similar to the training samples. This formulation encourages similarity, but it does not guarantee code compliance or mechanical safety. The loss function does not explicitly know whether an engineering requirement has been violated. We therefore modified both the training and generation formulations by introducing a constraint function, which I denote as C. The constraint function can contain design code requirements, engineering rules, and structural performance indicators. Knowledge and mechanics then participate in optimization rather than being checked only after generation. For gradient-based integration, the constraint function should be differentiable. Conventional finite element or structural design software is often difficult to differentiate directly. The neural network surrogate models developed in the optimization stage are therefore essential. We implemented this idea through a method called MAGIC, or Mask and Gradient Integrated Constraint Generative AI. Every time the length or thickness of a shear wall changes, a graph neural network surrogate can predict its flexural and shear stiffness and the derivative of those quantities with respect to the design variables. The gradient tells the generative process in which direction the wall should be modified to improve compliance. Depending on the problem, the differentiable constraint function can be provided by a surrogate model or a differentiable finite element formulation. In the case shown, the original method produced mechanically compliant designs in approximately 77.78% of the test cases. After mechanics-guided training and generation were introduced, the compliance ratio increased to approximately 100% for the indicator examined. The important point is that mechanics is no longer only a final check. It actively guides the generation process. Previous example involved one constraint. Real engineering design involves many potentially conflicting objectives: interstory drift, torsional response, axial compression ratio, flexural performance, shear performance, material use, and other requirements. Improving one indicator may make another worse. We therefore developed multi-objective coordination methods to determine reasonable trade-offs among several constraint gradients. The same concept can be applied to beam design. AI needs knowledge about where beams should and should not be placed. It also needs mechanical information about floor loads, vertical deformation, and the stiffness provided by the beam system. We combine data augmentation, annotations derived from engineers' experience, mask-based spatial constraints, load information, deformation prediction, and mechanics-guided evaluation. The output is a beam layout informed by data, knowledge, and mechanics together. For complex shear wall buildings, the resulting beam layouts were very similar to engineers' designs, with intersection over union values above 0.90. In an irregular frame example, the connection between the left and right portions of the structure was difficult. The engineer used a secondary beam, while the AI proposed a main beam connection that provided a more direct and mechanically favorable solution. This is an important change. The model is no longer merely imitating a historical drawing, it can produce an alternative with better structural performance. The fourth stage of our research is reasoning, particularly spatial reasoning. We now turn from computation to reasoning. The key question is how an AI system can move beyond a closed set of explicitly programmed constraints and use broader spatial and professional knowledge. When we compared current AI design with human design, we identified two remaining differences. First, current AI design mainly relies on data and computation. Human designers also reason. We compare alternatives and ask why one design is better than another. Second, most engineering AI systems have a relatively closed knowledge boundary. Human design can draw on much broader knowledge and common sense. In Hong Kong, for example, feng shui may influence an architectural decision significantly. More generally, users may express cultural, functional, or personal requirements that are not contained in a conventional dataset. Large language models provide one possible route for introducing this broader knowledge and reasoning capability. The computational core of a language model is the token. We input a sequence of tokens, and the model predicts the next token. Plain text can represent words and sentences very well, but how can it accurately represent an engineering drawing? We have a saying, a picture is worth 1,000 words. In fact, even 1,000 ordinary words may be insufficient to describe the geometry and relationships in a floor plan precisely. We therefore need new tokens that represent spatial information. We call them spatial tokens. In addition to the conventional language vocabulary, we define tokens for items such as the outline of a building, the geometry of rooms, room categories, and their spatial distribution. For example, a building outline can be discretized and represented as a sequence beginning with an outline start token, followed by learn geometry tokens, and ending with an outline end token. This provides a bridge between the geometric world of drawings and the token world of large models. Based on this idea, we developed a multimodal model called House Mind for architectural floor plan tasks. Because spatial tokens are not part of the original language model vocabulary, we first initialize and embed the new token representations. We then carry out full pre-training to align visual, geometric, and language modalities, followed by supervised fine-tuning for instruction-based tasks. After this three-stage process, the model can understand a design drawing, generate a floor plan from a request, and edit an existing plan according to instructions. The aim is not simply to produce an image that looks like a floor plan. The model reasons room by room so that room types, outlines, and relationships remain correct. In the comparison shown, the first column is the input building outline, the second is the ground truth, and the following columns show results from existing models and House Mind. We compared it with methods such as Tell2 Design, Chathouse Diffusion, Floorplan Llama, and Q1 Image Edit, and later with general image generation systems including GPT, Image 2 and Nano Banana Pro. In the cases shown, House Mind produced more accurate room-level layouts. This work was accepted by CVPR 2026. Another student subsequently developed a coordinate token representation for feature-sparse components. Floor plans can be abstracted into component-level line primitives and room-level polygon primitives. A vectorized sequence of coordinate tokens preserves the exact positions of sparse geometric components more compactly than a dense image representation. The coordinate position tokens preserve sparse component details and also improve room generation. In the experiments shown, this representation improved macro IOU by 27.8% and micro IOU by 21.3% compared with the VQVAE token representation. Each improved codebook gives the model a better connection between geometry and language. That concludes the part of the presentation concerned mainly with algorithmic research. I will now turn to real-world engineering applications. We did not want this research to remain only in academic papers, we wanted engineers to use it in actual projects. We therefore developed a platform called AI Structure Copilot, available through ai-structure.com. The system is installed as a plugin for CAD, so an engineer who is familiar with CAD can use it without learning an entirely new working environment. The user completes the initial setup locally and uploads the required design information. The cloud-based AI modules perform the design and return the results. The workflow includes initialization, layout design, member sizing, structural modeling, analysis, optimization, and material consumption evaluation. Given an architectural CAD drawing and design conditions, the outputs include structural component layouts, member sections, estimates of concrete and steel consumption, a structural analysis model, and a design report. The overall process typically takes approximately 15 to 20 minutes. To improve pre-processing efficiency, we use AI computer vision. The system identifies architectural walls, axes, windows, doors, and other components, vectorizes them, and converts the drawing into structured JSON information for the design model. This is important because architectural CAD drawings are often complex and are not immediately suitable as direct input to a generative model. Let me show a short demonstration. First, the user enters the design conditions and selects the architectural drawing. AI automatically identifies and preprocesses the architectural components. The user then starts structural design, and the system generates the component layout. With another command, it creates the structural model and performs the structural calculations. The report is returned to the user. The system can then optimize the structure and report material consumption and other indicators. Only a small number of user operations are required. An architect or a less experienced engineer can follow the process, while the AI and professional software perform the specialized calculations. By the time of this seminar, the platform had been used by more than 100 design institutes and in more than 5,000 engineering cases. The engineer's feedback is that it is particularly useful for quickly comparing and selecting preliminary structural schemes. The variety of cases shown on this slide also provides continuing feedback for the data flywheel. The example shown has project ID 5034. It is a 57-meter-high shear wall building designed for a seismic design intensity of 0.1 G. The AI-generated design passed evaluation by professional design software. The timestamp is around 4:27 in the afternoon. We have observed two peak periods of platform use, one shortly before 5 p.m. and another later in the evening. Without the software, an engineer might need to work overtime. With the software, the task can be completed much more quickly, and the engineer may be able to go home on time. The original question that motivated our work was, if AI can generate a realistic human face, why can it not generate a structural design that resembles one produced by an experienced engineer? Once building structure design became possible, the next question was, why should the method remain limited to that one discipline? Many engineering tasks involve generating drawings or spatial layouts. We therefore extended the approach to room layouts, strengthening existing buildings, infrastructure such as dams and bridges, photovoltaic support structures, and MEP systems such as fire sprinklers. The application objects are different, but the basic pattern remains similar: represent the design object, learn from data, generate alternatives, evaluate them with professional knowledge and mechanics, and optimize the result. A design institute contains different disciplines. Architects and structural engineers may have conflicting requirements, and repeated coordination can reduce efficiency. An architect may say, "Do not place a column here," while the structural engineer says, "A column is needed here." Existing intelligent design systems also have limitations. They often focus on simple house types and may not generate key architectural components such as doors and windows. We therefore began to integrate architectural floor plan generation with structural design. Local design customs are important. The arrangement preferred in Japan may differ from that preferred in Hong Kong or the Chinese mainland. In many locations, however, only a small local dataset is available. We addressed this problem through transfer learning. A general model is first pre-trained on a large common dataset containing more than 80,000 plans. A much smaller local dataset, Japanese housing plans, for example, is then used for fine-tuning. In the experiment shown, transfer learning improved micro-IOU and macro-IOU by approximately 300.9% and 532.3%, respectively, compared with direct training on the small dataset. After generating the room layout, we use coordinate position tokens to design doors and windows. The multimodal model receives the building outline, floor plan design, and an instruction, and then generates a sequence representing the door and window locations. In the reported cases, the door IOU was approximately 0.8324, the window IOU was approximately 0.8707, and the location F1 score reached approximately 0.95. The architectural layout then becomes the input to the structural system. A diffusion model and a heterogeneous graph neural network are used for column layout, beam generation, and member sizing. The complete chain includes the floor plan, doors and windows, columns, beams, member sections, automated structural modeling, performance evaluation, and compliance checking. For the three-story independent residential building shown, the process begins with the floor envelope and functional topology, then generates room layouts, doors and windows, columns and beams, and the analytical model. Engineers can review and fine-tune the AI result. In this case, the architectural design time was reduced by approximately 85.2%, and the structural design time was reduced by approximately 96.1%. The software interface allows the user to specify the building outline, number of stories, family members, budget, bedrooms, bathrooms, and the required rooms and their relationships. For example, the user may require the bathroom to be close to the bedroom or a reading room to be adjacent to another functional space. The system displays the generated design and allows the user to edit it. Let me show the floor plan generation and editing platform. The user draws or uploads the building outline and specifies the rooms and their topological relationships. The model generates a room layout together with doors and windows. If the user wants to add a storage room, the new requirement can be inserted through an instruction. If the user wants a local change, that request can be expressed in natural language. The system modifies the designated region and updates the room topology while retaining the rest of the design as far as possible. A multimodal large model can also generate facade renderings from the design sketch. The architectural sketch and background image are combined with a textual prompt, and the model generates a rendering corresponding to the requested style and context. Through this chain of tools, even a non-specialist user can participate directly in the early design of a house. This may change the business model of the design industry. In the conventional process, the client contacts an architect, the architect develops the scheme, and the structural engineer then develops and checks the structure. Single-discipline AI can make the structural stage faster and reduce cost. Integrated architectural and structural AI may go further by enabling the Design Institute to serve a much larger number of clients, including individual clients, while retaining professional review and approval. We also applied generative design to the strengthening of aging frame structures using buckling restraint braces, or BRBS. The placement of BRBS must satisfy two very different types of requirements. Architectural constraints, stairs, corridors, bathrooms, doors, and functional spaces, determine where a brace is feasible. Structural constraints determine where braces are needed for seismic performance. Architectural constraints are difficult to express completely as equations, while structural constraints must be quantitatively evaluated. We therefore divide the process into two stages. In the first stage, generative AI learns from existing architectural layouts and identifies feasible brace positions according to the architectural constraints. In the second stage, mechanics and rule-guided optimization selects the final BRB layout according to structural performance requirements. This separates a difficult qualitative feasibility problem from the quantitative structural optimization problem. For the typical three-story case shown, the system first generated feasible brace positions and then selected the final design. The complete design took approximately 15 minutes and satisfied the code requirements while respecting the architectural constraints. We then extended the method from buildings to infrastructure, including concrete-faced rock-fill dams. A concrete-faced rock-fill dam contains several functional zones, including the cushion, transition, primary rock-fill, secondary rock-fill, drainage, and modulus increased zones. Zoning design is a crucial and demanding part of the dam cross-sectional design. For this problem, we moved from an image-based representation to a compact parameter-based representation. Key geometric parameters describe the dam and zoning boundaries. When the geometry and material variables are combined, the design is represented in a stable and interpretable 32-dimensional latent space for diffusion generation. This reduces the dimensionality while preserving physically meaningful variables. The main difficulty is data scarcity. We collected only 53 high-quality real designs, which is not enough for direct training of a complex generative model. We therefore used a two-stage strategy. First, parameterized generation produced approximately 10,000 synthetic cases. These lower-quality cases allowed the model to learn the basic geometry and patterns of dam zoning. Second, the 53 high-quality real cases were used for fine-tuning so that the model could learn actual engineering experience. A dam design must satisfy anti-sliding stability, deformation, and other mechanical requirements while controlling cost. We developed surrogate models with a common residential net 1D architecture. The input combines geometric and material channels, and the outputs include the minimum factor of safety and deformation-related quantities. These models provide rapid mechanical evaluations for generative design and optimization. The stability, deformation, parameter realism, and economy objectives may conflict. We therefore perform multi-objective fusion in a 10-dimensional key-parameter space. When a design fails to meet a code limit, the corresponding compliance metric and gradient guide the correction. When all limits are satisfied, the objective weights can shift toward economy and other design goals. This allows parameter-level resolution of mechanical conflicts. The data-driven and mechanics-embedded designs both resemble the engineer's design. However, after mechanics was embedded in the diffusion process, the design in the comparison shown achieved approximately 17.8% better economy while satisfying the relevant limits. This demonstrates again that the model should not merely imitate historical data. Mechanics can guide it toward a better solution. The input geometry is converted into an AI zoning design. The system then reports similarity to engineering designs and evaluates the stability safety factor. The two-dimensional zoning result can also be combined with terrain information to generate a three-dimensional dam model. A design report can subsequently be generated automatically. Let me show the CAD-based workflow. The engineer starts a design project and enters the terrain, dam geometry, material information, and design parameters. The AI generates the zoning scheme, evaluates the mechanical indicators, and displays the two-dimensional and three-dimensional results. This work was jointly developed with Power China so that the research method could be connected to an actual engineering workflow. We have also applied the generation, evaluation, optimization workflow to photovoltaic support structures. AI first learns from existing drawings and generates a support structure design resembling an engineer's solution. A finite elements solver then evaluates and optimizes the design. In the cases shown, AI generation reduced the design time from approximately 60 minutes to about 1 minute while producing a comparable cost level. The user begins by entering the project information. The system then generates the support structure, performs structural optimization, designs the pile foundations, and calculates the cost. Compared with manual design, the AI-assisted process increased efficiency by approximately 50 to 60 times in the cases shown. At the time of this seminar, this remained an active research and development direction. Together with colleagues at the Hong Kong Polytechnic University, we applied generative AI to fire sprinkler layout design. Every room requires appropriate sprinkler coverage. The model learns from architectural drawings and corresponding sprinkler design drawings, then generates a layout for a new plan. In the case shown, the AI design was very similar to the engineer's design. The engineer required approximately 21 minutes, while the AI generated its result in about 10 seconds. Generative AI can greatly reduce the time required for the initial layout. The method has also been extended to concrete continuous bridges, including cross-sectional design and the layout of prestressing tendons. The preliminary results show layouts similar to those prepared by engineers. When many design models and design stages become available, workflow organization itself becomes a research question. As a preliminary exploration, we developed an open-source framework called StructureClaw. Existing models often perform isolated generation. The purpose here is to connect generation, revision, analysis, and verification in a traceable loop. The framework uses a reasoning and acting process to interpret a natural language design request, identify missing information, select an engineering skill or tool, execute a step, inspect the returned result, and continue to the next step. The aim is to connect otherwise isolated design tasks while retaining verified artifacts such as the structural model and analysis results. The StructureClaw platform is open source, so researchers and engineers can use it and contribute additional skills and tools. That completes the application examples. Let me finish with several conclusions and thoughts for discussion. Over the past several years, this work has received recognition from both research and industry communities. Examples include the International First Prize of the Hong Kong Construction Industry Council Innovation Award in 2022, the Gold Medal with congratulations of the jury at the International Exhibition of Inventions of Geneva in 2023, and selection by China's Ministry of Industry and Information Technology as a typical application of AI empowering new industrialization in 2024, an outstanding high-quality industry dataset achievement at the World Artificial Intelligence Conference, WAIC 2026. We have also received recognition for jointly developed intelligent structural design systems. This year marks approximately 30 years since I entered university and began my education as a civil engineer. During those 30 years, my colleagues and I learned structural mechanics, design codes, physical laws, professional knowledge, engineering experience, and many design drawings. Although today I have spoken extensively about AI, the foundation of the work is not AI alone. It is the combination of mechanics, physical laws, professional knowledge, design experience, and high-quality engineering data. This gives structural engineers an important opportunity. We can connect the accumulated knowledge of our discipline with new AI capabilities and create a research field that belongs neither to generic AI alone nor to conventional structural engineering alone. AI design has several distinctive features. Once an AI system has learned a capability, it does not forget it in the same way a person may. The capability can be replicated at scale. A task can be completed in seconds, and the system can be available 24 hours a day, 7 days a week. This leads to a vision that has motivated our work, a master-level mentor for every young engineer and a tireless assistant for every engineer. Perhaps one day we can train an AI system that captures part of the capability of great structural engineers. It could help young engineers learn, support practicing engineers in difficult work, and reduce overtime. That concludes my presentation. Thank you very much for your attention. I would be very happy to discuss the work and answer your questions.